This video is for Physics of the Universe, Unit 1.1, Understanding and Describing Motion. Today's essential question is, what are frames of reference, and how do they relate to motion? Hello, baby birds! Today, we are starting our journey into one of the most foundational building blocks of physics, frames of reference. This concept underpins everything that we'll study in motion and mechanics. Whether you realize it or not, every time you talk about how fast something is going, or where it is, you are already using a frame of reference. You are measuring that object's position or speed relative to something else. Maybe a moving car, maybe the ground, or even the stars themselves. In this video, we'll break down what a frame of reference is, why it matters so much in physics, and how we can apply it in both everyday situations and in scientific analyses. To make these ideas come to life, we'll explore real-world examples like tossing a ball while on a train, tracking a flying butterfly, and navigating a spacecraft. A frame of reference is more than just a concept. It's a mental and mathematical tool that allows us to describe where things are and how they move. Imagine that you're in a room with invisible graph paper stretched in all directions. That grid has an origin, usually called the 0 point, and 3 axes, x, y, and z. When we place an object somewhere, we give it coordinates based on how far it is from these axes. But there's more to it than that. A frame of reference also includes a perspective, which means a specific viewpoint. From that specific viewpoint, we watch how an object's position changes over time. That change is what we call motion. But without a defined origin or axes, we can't say anything meaningful about that change. For instance, saying, quote, the ball moved 5 meters, end quote, means nothing unless we say 5 meters relative to what? The wall? The floor? Some other moving object? The key idea here is motion is always described relative to a chosen frame of reference. One of the most profound ideas in physics is that motion is in fact relative. That means the same motion can appear very different depending on your viewpoint. So let's walk through an anchoring event that really illustrates this. Imagine you're on a high-speed train traveling at 300 kilometers per hour. You toss a ball straight up. What happens? From your point of view, which is inside the train, the ball goes straight up and comes right back down into your hand. But to someone standing outside the train, on the platform or on the ground, the ball doesn't go up and straight up and down. It follows a curved path from their perspective, like an arc. So, who is right? It turns out both are. Because each observer is using a different frame of reference, both are correct. This is why understanding and choosing an appropriate frame is so important. A good frame simplifies your problem, helps you make accurate predictions, and allows you to communicate clearly. So let's categorize the different types of frames of reference. First, there's a stationary frame, which is fixed and doesn't move. Think about the classroom that you inhabit. If you drop a pencil, it falls to the floor relative to the classroom. The classroom becomes your frame of reference. Second, there's a moving frame, which is one that travels with a constant velocity. Trains, cars, airplanes, even elevators can be moving frames. And thirdly, a rotating frame is a frame that spins. Earth is a great example of this. Even though it feels like we're standing still, Earth is rotating on its axis and orbiting the sun at incredible speeds. Each of these frames offers different insights. For example, observing a spinning object from a rotating frame will look different than observing it from a stationary one. And in some cases, Choosing one frame above another can turn a hard problem into an easy one. Now let's drill down into an even more important distinction: inertial versus non-inertial frames. An inertial frame is one that moves at a constant velocity, meaning it's either at rest or moving in a straight line at a steady speed. In these frames, Newton's laws of motion hold true without any modification. A perfect example is a train cruising smoothly on straight tracks. Inside the train, if you drop a pin, it falls straight down, just like it would on the ground. But then there's a non-inertial frame. This type of frame is accelerating, which means it's either speeding up, slowing down, or changing directions. In these non-inertial frames, things can get weird. Forces seem to appear out of nowhere. We call these fictitious forces because they're not caused by any physical interaction, but by the acceleration of the frame itself. For example, when a car takes a sharp turn, you feel like you're being thrown to the side. That sensation isn't caused by a real force, it's the result of your non-inertial frame of reference. These fictitious forces help us understand motion from within a non-inertial frame, but they don't exist in the same way as gravity or friction. Now let's look at how many dimensions an object can move in. We have one-dimensional motion, which happens along a single axis. If a ball drops straight down, only the y-axis is changing. But there's two-dimensional motion, which occurs when an object moves in a plane, like a paper airplane flying across the room. In this case, now the x and y axes are changing. Then there's three-dimensional motion, which is more complex. It's when the object's position changes along all three axes, x, y, and z. Think of a butterfly moving around the room, or a drone rising, spinning, and then moving forward. We can take a look at a sample calculation from the example of a drone. Suppose that a drone starts at position 1, 2, 0 and ends at position 4, 5, 2. To find the displacement, we calculate the difference in each coordinate. Our delta x is going to be 4 minus 1, which is 3 meters. Delta y is 5 minus 2, which is also 3 meters. But then delta z is 2 minus 0, which is 2 meters. Then we find the magnitude of that displacement vector using the Pythagorean theorem, which ends up being the square root of 3 squared plus 3 squared plus 2 squared, which is the square root of 9 plus 4, which is the square root of 22, which ends up being around 4.7. This 3D analysis is only possible because we're using a well-defined coordinate system. Your classroom is a perfect real-world example of a frame of reference. First, you pick a corner of the room as the origin. This is where your 0, 0, 0 point will be. Then, use the floor and walls to define your x, y, and z axes. Finally, use this grid to describe the position of any object, a backpack, a chair, or a drone. Now let's look at how these concepts show up in the real world. In an airplane, if you toss a ball straight up while flying at 500 miles per hour, it still lands in your hand. But to an observer on the ground, the ball traces an arc through the air. In a moving car, if you drop something out the window, it appears to fall straight down from your hand, but it actually shoots backwards relative to the road. On Earth, weather patterns like hurricanes are influenced by its rotation, which in part is a rotating frame. But then there's a spacecraft that navigates in a constantly changing frame. NASA engineers often use multiple frames at once. One frame that is fixed to Earth, and then another that is fixed to the spacecraft. Understanding these situations means shifting your frame of reference and seeing motion from multiple perspectives. Before we move on, let's clear up some common misunderstandings. Some students believe that there is only one correct frame. In reality, multiple frames can be valid for describing the same motion. Others confuse distance with displacement. Distance is a scalar quantity, meaning it only has magnitude, while displacement is a vector. It includes both magnitude and direction. Similarly, speed and velocity are also often mixed up. Speed is scalar and velocity is vector. Finally, people often think Earth is perfectly stationary, but Earth spins on its axis and orbits the sun, meaning it's constantly in motion. Fortunately, the effects of this movement are usually negligible for classroom experiments. Remember, physics is not about memorizing answers. It's about choosing the right perspective. So let's wrap up everything we've discussed so far in this video. Motion is relative. How we see motion depends entirely on our frame of reference. Multiple valid frames exist, meaning there isn't one true frame. Different frames offer different advantages. We need to choose wisely. Some frames make calculations easier and interpretations clearer. And then we want to be able to connect this to life. You are constantly switching frames in everyday life, when walking, driving, flying, or even turning your head. A frame of reference is more than just a physics tool. It's a mindset. It teaches us that truth can depend on perspective, and that the key to understanding motion is choosing the best lens to view it through. At this point, you should be able to generate a full and appropriate response to today's essential question. What are frames of reference, and how do they relate to motion?